So this video is going to take you through 3 examples or worked examples on solving orbital problems. So let's deal, and remember what we're using are either t squared is proportional to r cubed, which is what we can use if we're going to work with ratios, or if we want to solve it more correctly, we would go, well, not necessarily more correctly, but more in terms of using Newton's laws of gravitation. T squared equals 4 pi squared over gm times r cubed, where m is the mass of the body that you're in orbit around, and that's sort of assuming you're in a circular orbit, which is what we're going to work with now. So let's do a few little example problems. Let's do number 1. Let's do an asteroid is, let's say it is 3.2 AU from the Sun. What is its orbital period? Now, I'm going to just solve this both ways just to show that they are the same. So the first is, let's use the ratio method, the method that Kepler would have used to solve the problem, which is to say, okay, so we can say that we know that t squared is proportional to r cubed. And if we work in years, okay, that would allow us to say that t of the asteroid squared over the time period for the Earth squared is equal to r of the asteroid cubed over the time period of the Earth cubed. Now, given that we can work in astronomical units in the year, well, these values are both equal to 1, either 1 AU or 1 year. So that would allow us to say that the time period is equal to the square root of 3.2 cubed, and what we end up with that is 3.2 cubed. We'll root that answer and we get 5.7 years. Now, if we were dealing with a scenario where we didn't necessarily weren't given it in AU, or where you could sit there and say, okay, well, we can say that we could also say t squared is equal to 4 pi squared over gm r cubed. So what we want is the t squared is equal to 4 pi squared over g is 6.67 times 10 to the minus 11. The mass of the Sun, which you would be given in order to solve this problem, is 2 times 10 to the 30, and we're after, the radius, but we need this to be in meters. So we've got 1 AU that would be given to you. It's in the data book. Is 1.5 times 10 to the 11. So we've got 3.2 times 1.5 times 10 to the 11, and that radius is cubed. So I'm going to type this out on my calculator and hope I get the same number. 3.2 times 1.5, 3.2 times 1.5 e to the 11. Let's cube that. 4 over 6.67 e to the minus 11 over 2 e to 30, and what we get is 3.3 times 10 to the 16. We have to square root that. And I get 181 times 10 to the 6. That's in seconds. And 1 year is equal to 3.1 5 times 10 to the 7 seconds. So over 3.157, and I get 5. So that, if I divide this number by that, I get t equals 5.7 years, which is the same answer. Hooray! You might get some differences at the higher numbers of decimal places, but that's because of rounding and rounding errors largely. So that's how we can solve that kind of problem. Let's deal with other things. Let's deal with satellites. That's not spelled correctly. It's upsetting. There's only one. I wrote that and I went, nope. Okay, so satellites are things that generally either orbit planets or moons or things. We just put them around them. A moon is a satellite. So now the thing is that what we can't do for these, we cannot use. So for these, we cannot use directly. We can't just say t squared is equal to r cubed, because that only works if we're dealing with comparing with the Earth and just going around the sun, because we aren't going around the sun. Okay, so we can't do that directly. So normally with satellites, you would be using the full equation. Okay, so as an example, we can say the ISS an orbit 400 kilometers above the surface of the Earth. What is its orbit time? And now the thing for that is it's important to recognize that that when they say this, they go, oh, it's above the surface of the Earth. So it's a distance that you have to add to the radius of the Earth. So the information you would need for this is the radius of the Earth is equal to 6,400 kilometers, and the mass of the Earth is equal to 6 times 10 to the 24 kilograms. So we can do that. We can say t squared is equal to 4 pi squared over gm times r cubed. Now for r is equal to 6,400 plus 400, so that equals 6.8 times 10 to the 6 meters. Got to convert into meters if we're going to deal with seconds, and so we end up there with t squared is equal to 4 pi squared over 6.67 times 10 to the minus 11 times 6 times 10 to the 24 times 6.8 times 10 to the 6, and that is cubed. Throw that in. Cube that. And what you get there is 31 times 10 to the 6 seconds squared. So t is equal to the square root of 31 times 10 to the 6. We end up with about 5,600 seconds, which if you divide by 60, you get around 92 minutes, or 93 minutes. So 93 minutes is still, that's quite quick. That's how long it takes. If you see the International Space Station and if it's a good clear night for observing, if you wait 93 minutes, you'll see it again, going in its orbit around the Earth. If we wanted to know what is the speed of that orbit, well, we could do 2 pi r over t, and we could do, so 2 times pi times r is 6.8 times 10 to the 6 over 5,600, and you get 7 point something kilometers. So 2 8.86 over 5,600. You get about 7.6 kilometers per second. So pretty fast. It's not quite the 11 that you need to escape from, but it's quite good, in terms of that. So that's sort of like solving an orbit motion. Now, one of the things that is important is there's a specific type of orbit that you kind of need to know about, okay, and that is it's called a geostationary orbit. Now, for communication purposes, what we need are a series of satellites that do not appear to drift. Okay, so if you are, if you're standing sort of here and you look at a patch of the sky, that you'll see a satellite. Okay, that satellite is going beep. And what you need is that when you come back 24 hours later, that satellite must be in the same patch of the sky. What it can't be is suddenly over there. Okay, so you're going to go round the Earth because the Earth is going to rotate. You need this thing to rotate with you because it has to be in a fixed position. Why? Because we are communicating with it. You're sending signals to it. It's sending signals back, which is how your communication systems work. But what you can't have is a system where if it drifts, then you're going to miss it. Or you're going to have to constantly calibrate our transmitter arrays in order to know where these things are. And so it's much easier to put it somewhere where it's going to be stationary. Okay, and so it's called geostationary. It's stationary with respect to the Earth. Now that means that it's going to have an orbital period of 24 hours. It also means a couple of other things. It has to be in a certain location. It has to be sitting above the equator, because otherwise it drifts because of it will be at an orbit aligned the equator. So, if you have a position where you're not, then what it will do is so if you have the Earth, and let's say there's the equator. If you have a satellite that's kind of there, then as it orbits, it's going to sort of swing round and be sort of, sometimes it's going to be appearing in the northern hemisphere and sometimes in the southern hemisphere. That's no good either. What you need is something that's going to be in an orbit that means it's going to go sort of around like that. And that means that we're always going to know where it is. So that's kind of the conditions. So a geostationary I spelt it wrong again. That's very, very bad. Boo. I don't know why I'm suddenly doing that. Satellite. Will always be in a fixed position in the sky. This is achieved by, and there are three things that need to happen. So it needs to be in orbit above the equator. That's a terrible word, but that means equator. Orbiting in the same direction as the Earth. I mean, you could send it the other way around. You would annoy everyone else who's put a satellite in a geostationary orbit because you'd crash into the wall. So don't do that. Make sure you're going in the right way, or the Earth's rotation, I should say. And finally has a period of 24 hours, which is 86,400 seconds. Just so you are aware, it's not exactly that. There's two different types of day. There's a solar day and a sidereal day. Sidereal day is actually 23 hours and 56 minutes. So that's what it really is. But as far as the A-level is concerned, you've never heard me say that. So it's 86,400 seconds. Now, to therefore work out where that must be, we can say, so the orbit height is therefore, so we've got t squared is equal to 4 pi squared over gm r cubed. Rearrange that slightly so we get r cubed is equal to t squared times g times m over 4 pi squared. Put on our values. Apologies, have to redo a little bit because someone phoned. So what we have there is where are we? So r cubed is equal to 86,400 times 6.6 squared times 6.67 times 10 to the minus 11 times 6 times 10 to the 24 all over 4 pi squared. So what you end up with there is 86,400 squared times 6.67 e to the minus 11 times 6 e to the 24 over 4 over pi squared, and we get 7.6 times 10 to the 22. So r is going to be the cube root of that. So we cube root, the radius is the cube root of that. So we take the cube root and we get 42 times 10 to the 6 meters. Now that's a fairly sizable distance. Okay. So the radius, remember the radius of the Earth is, so if you've got the Earth, the radius of the Earth is 6.4 times 10 to the 6. So you are, you're about another 6.5 Earth distances above. Okay, so your satellite that is sort of here is around another 6.5 Earth sort of distances above. If we want to do that in sort of meters that you are standing above you, well, that is a distance of 42 e to the 6 minus 6.4 e to the 6. What you've got is 36. Pens off. So you've got that as 36 times 10 to the 6 meters. Now, if you think about what that means in terms of, say, a time delay, like, you're sending a message out there and back again. So you're sending a signal to a satellite, it's that distance. You've got to double that because it's got to go there and back again, and you're going to get that as about So you've got to go a total distance of 71 times 10 to the 6 meters. And you're going to do that at the speed of light, which is 3 times 10 to the 8. And you're still going to really be looking at about 0. So that's going to take about 0.224 seconds. Now, just to put your mind in context about something about like this level of distance, you might remember a long time ago when you were in year 9, you were taken to the field to measure the speed of sound, and you went by the long jump pit, and you all sort of stood there. And if it was me that took you out there, or maybe another member of staff, you had another member of staff sort of over there, and they would fire the gun, and you would see some kind of signal that would drift across there, and then you'd hear the sound. Now, that distance to get from sort of across the field, that was roughly about 0.4 seconds-ish, something in that kind of order of magnitude. So, in order to have a geostationary satellite, to talk to a geostationary satellite, not accounting for processing time and things, is still quicker with the speed of light than it is to yell across the school sports field to somebody on the other side of it. It's about twice as quick, because actually more than that, because that signal will have to go there and then come back again. So it's quite significant. That's the kind of distances you need to get to start noticing a sort of delay in a signal coming back to you. Now, just one final thing to finish off, which is a reminder that you can still use t squared is proportional to r cubed. And this is something that sometimes happens if you don't know the mass of the planet you're going around, but you do know some things, because this relationship is fine as long as you have enough information. Because for any two things, as long as they're orbiting the same body, that would tell you that T1 over T2 squared is equal to R1 over R2 cubed. Okay, and we can see that for the data we've just collected for the ISS and a geostationary satellite. For the ISS, we'll put the geostationary satellite on top because they're the bigger numbers. But the time for a geostationary satellite was 86,400. And the time period for the ISS was about 5,600 seconds. And if we square that, we get 86,400 over 5,600 squared. We get about 240. That's my ratio. If I do the radius of the geostationary satellite, which was 42 times 10 to the 6, and I divide that by the radius of the ISS, which is 6.8 times 10 to the 6, and I cube that, so I get 42 e to the 6 over 6.8 e to the 6, it's 117, cube it, and I get 200 and, basically 2 sig figs, I get 240, which isn't surprising because physics works. And there we go. That's gravity.